Hi folks, today we're going to talk about the theory of evolution by natural selection. The theory of evolution came from thinking about the long-term effects of millions of years of natural selection on species. So imagine any species. Where did it come from? How did it get here? Could its traits have been naturally selected over time? Could the environment have changed which members of the species were more likely to survive? If so, then the species has definitely changed at least once. And who's to say it didn't change from something before that? If we follow that line of thinking, we can see that the species might have changed multiple times over millions of years. Evolution is a scientific theory that says that all species were created by a change in an older species. Evolution is nothing more than the change of a species over a long period of time. Structural data, DNA, developmental patterns, and fossils are all pieces of evidence that support the theory that populations can change over time. Fossils. They're the remains or imprints of a once living organism. They usually form when a dead organism is covered by a layer of sediment or mud, and then over time more sediment settles on top of that organism. Minerals in the sediment may seep into the organism and replace the body's material with minerals that harden over time. Fossils can be found as mineral deposits in sedimentary rock, or they could be preserved fossils, like a fossil that's in the remains of an amber, or maybe a fossil that's preserved in ice. When it comes to digging for fossils and studying rocks, the basic concept is the deeper it is in the ground, the older it is. The fossil record consists of all of the fossils that have ever been discovered. As we look at different species changing over time, we might see that we have gaps in our fossil record. Any fossil that helps us to understand those changes between the species are called transitional fossils. They fill in those gaps. And when we're looking at the fossil record of a similar organism, we can see the transition from one species to the next. When we consider that a species can change, we can think about a species as having come from another, which we might call an ancestor. Similar to how you have ancestors like your parents and your grandparents and your great-grandparents. So anytime that we see different species sharing an ancestor, we can call that ancestor a common ancestor. It's kind of like how you and your cousin both have the same grandparent, but you don't come from the same parents. If we look at this simple chart of different species over time, we can see that if you go back far enough in their histories, those two purple species at the bottom share a common ancestor, the pink one at the top. Biologists can observe that all living organisms share some traits in common, and they inherit traits in similar ways. When we look at the structural data of two different organisms, we can compare their bone structures, and we might find some odd similarities. For example, snakes have traces of a leg-like structure that isn't used for movement today. And this supports the idea that they're related to other animals, like lizards or maybe even dogs. DNA is another piece of evidence for evolution. Scientists can compare the DNA from two different living organisms. The greater the similarities are in the DNA, or the more similar the DNA is, the more closely those organisms are likely related to each other. DNA determines which amino acids get to make up a protein. In our bodies, there are 20 different amino acids. If we look at cytochrome C, which is our example here, it looks at the specific differences in that one amino acid. It's not saying that chimpanzees and rhesus monkeys are exactly the same as humans, and it's not saying that yeast has nothing in common with humans. It's simply saying that in this one amino acid, yeast has 42 differences in that cytochrome C amino acid than humans. And when we compare humans to the rhesus monkey or chimpanzee, we only see 1 or 0 differences in that one of our 20 amino acids. So that tells us that we are most likely much more related to chimpanzees and rhesus monkeys than we are yeast or bacteria. And we already know that just from looking at each other. We have 4 appendages, 2 arms, 2 legs, so do the rhesus monkey. We have teeth. Bacteria doesn't have teeth. We have all sorts of similarities that we can see within each other, so obviously our DNA must be pretty similar too. Lastly, if we look at developmental patterns, or in other words, how an organism grows as it's being formed, we usually study the embryos of different organisms, and that's called embryology. But as the embryo develops, they undergo many physical and functional changes. If organisms develop in similar ways, they also likely share a common ancestor. For example, all animals with backbones have a tail at some point during development. You notice that even humans had gills as an embryo at some point in our development, and then we grew out of them before we're born. This leads to the idea that we are somehow related to some other species that has gills and a tail. There are a lot of misconceptions about evolution, and I'd like to tackle them as you have questions about them. One example of a misconception about evolution is that evolution says that humans come from monkeys. That's completely untrue. Evolution says that somewhere along our evolutionary history, apes and humans shared a common ancestor. And then somehow the species changed a little bit, and the apes went this way and turned into smaller apes or monkeys. And this way, humans developed. So we branch off like a family tree, and differences are made. But somewhere down the line, there was a common ancestor. If you have any other questions about evolution that wasn't cleared up in this video, please feel free to ask me in class. I'd love to enlighten you.